see a particular pH, that's usually where the proteins that function in that region, that's the pH they work best in. Okay?
What is the function of trypsin?
Trypsin is what we call a protease. It breaks apart proteins after certain amino acids. Same thing with pepsin. Pepsin also does that, breaks apart proteins. Okay, does anybody have a question or can I repeat anything? All right. We'll talk about protein structure and function in great detail in a couple of lectures from now. But what I want to show you is how the amino acids that make up proteins, amino acids themselves, as the term indicates, amino acids are acids. And they can donate hydrogen ions to the cellular background. They exist as what we call dipolar ions. They can act as both a proton donor and acceptor. So for example, this is an amino acid. This is an amino acid. This is what we call the alpha carbon. The alpha carbon of an amino acid is always covalently bonded to an amino group, to a hydrogen, to a organic chemical group that's indicated by R. And we'll look at these various different organic chemical groups when we talk about amino acid structure in a couple of lectures. And the alpha carbon is also covalently bonded to what we call a carboxyl group, indicated here. And so consequently, this carboxyls are also called carboxylic acids, and they can donate hydrogen to the background. The amino group, on the other hand, can function as a base. It can actually accept a hydrogen ion. And so in the non-ionic form, this is what you have. Usually in a cellular background, amino acids exist in an ionic form, where you have ammonia and a ionized carboxylic acid shown here. Okay? It's called the zwitterionic form because it has two ionic forms, negatively charged and positively charged. Okay? All right. What I want to also stress is that these are called functional groups. These are called functional groups. And they're going to affect the chemical environment. The functional groups that you find on amino acids will affect the structure and function of enzymes that they make up. What you're looking at here is glutamate. This is the amino acid glutamate. Here's the alpha carbon. Here's the carboxylic acid group, the amino group, the hydrogen, and then the R group of glutamate, this organic group right here, shown here. What's interesting about glutamate is the R group actually contains a carboxylic acid. It contains a carboxylic acid, and so glutamate is considered an acidic amino acid, and it can actually undergo ionization. The first point where a glutamate will undergo ionization in one of your cells, it will undergo ionization first at the carboxylic acid, shown here. The next point where the glutamate will undergo ionization is within its R group. That's called its PKR. A PKR is where you have an amino acid that has an R group that can undergo ionization, and that's what this will do, and lose its hydrogen to the environment. And then finally, glutamate can actually lose its hydrogen from its amino group to become a completely unionized or ionized only on its carboxylic acids, shown here. But what's interesting is where this happens. What would be the background pHs for glutamate to undergo ionization from first this carboxylic acid, then the carboxylic acid on its R group, and then finally from its amino group. And the background pHs are shown here. So pK1, background pH is 2.19, really low. For the pKr, or ionization of the R group, you're looking at a background pH of 4.25. And finally, for ionization of the amino group, you're looking at a background pH of 9.67. Okay? So do any of these actually ionize very easily in a cellular background? No, not easily. Most of the kind of titration that I've shown here, this would be done if you were using pure glutamate in the laboratory on the laboratory bench. And you get a similar situation with another amino acid. The other amino acid is histidine. Histidine, of all of the amino acids, we have 20 different amino acids that combine to form all of our different proteins. Histidine is the only amino acid we have that can buffer at cellular pH, and that's because, and look at this fancy R group that histidine has, very fancy R group, but the pKr, or the background pH that will allow histidine to actually donate a hydrogen, would be this hydrogen right here, to the environment, is a background pH of 6.0. So that's right within the blood, it's right within the cytoplasm of the cell. So histidine is the only amino acid that can actually function as a buffer in our cellular background and in our blood. And so consequently, histidine is an amino acid that you find oftentimes on the surface of proteins. Histidine is an amino acid that you'll find oftentimes on the surface of proteins because it has this buffering capacity. So pK1 just refers to the hydrogen that would be ionized from the carboxyl shown here. pKr is the hydrogen that would be ionized from the amino group shown here. And this would be the R group of histidine. And then finally, pK2 is the hydrogen that would be ionized from the amino shown here. And what you'll see again is very similar to the kind of titration curve that we see with glutamate. pK1 is usually a low background pH. pKr, in the case of histidine, is close to what you find in blood and the cytoplasm of cells. And then pK2 always is very, very high. Okay? All right. And what you see here is a list of different amino acids. And what you also see is the amino acids that actually have a pKr. Not all amino acids have a pKr because many of our amino acids have an R group. This R group that I was talking about here, many amino acids have R groups that are not ionizing. Only amino acids that have an R group that is ionizable will actually